You're listening to the Knowledge Archives podcast. Welcome to the Knowledge Archives podcast. We're a group of students on a mission to learn from as many different disciplines of knowledge as possible. I'm your host, Madhav Malhotra, and today I'm lucky to be joined by Dr. Gerald Corzo, Associate Professor of Hydroinformatics at the Delft Institute for Water Education in the Netherlands. His research focuses on using tools like artificial intelligence to model water resources in the context of floods, droughts, and other hydrological phenomena. I'm very curious about this important field and how it has grown in the past few decades. Thank you for joining me today. I'm looking forward to learning a lot more about your work. I'm very interested in all the complicated details and interdisciplinary connections. But first of all, I'd just love to ask you to quickly introduce yourself and how you got started in this area of work.
Okay, thank you, Mata, for inviting me to this podcast. Well, I'm originally from Colombia and I studied civil engineering. And my passion since I was little was always to program. So I have been doing a lot of computer science before even the software engineering career started. So when I started were the first careers of software engineering, but I was already doing a lot of things in my civil engineering background. So when I graduated, I didn't have this data certification. And I was already starting to teach at the university, and I felt that I needed that to move forward. So I did a specialization. And then I felt happy. In fact, they almost didn't receive me into this program because they say civil engineers don't know anything about systems. And they told me that I might fail. But suddenly, since I was really happy with that, I got the best marks. So they were really happy with me. And that moved me even more towards computer science. And then I moved to a Master of Science in Hydroinformatics. And that's where I started this interaction. I did my master, so it was quite good, my performance. I was really happy doing things with data-driven machine learning. I started to learn machine learning when I arrived here to the Netherlands in 2003. Also, I managed to develop some mixture of expert models for forecasting. That was my first approach to machine learning. That I was challenged by the idea that you can do the things with data. And with that, I got funds, a scholarship from a project to do my PhD. And I started these hybrid models, what I was telling you, trying to link between data and the hydrological concepts and the processes and all the work that has been done. And since then, I graduated from a PhD. I did a postdoc at the University of Wageningen. And I was working with a big project called Watch. It was all over the world about climate change. We were making analysis of droughts. They liked my profile when they hired me because it was interesting that the project was leading droughts, but I was expert in floods. But they found that was also this data part, and they were working with big data, very, very big data. The models can take 6 months on running, and then you have terabytes. And then my background of software engineering and all these things fitted perfect. So I started to develop slowly, and I'm really happy still doing that.
Mm-hmm. And when someone else looks into your background from the outside, it's just incredible to see all of these different expertises you have with the AI side of things, with the hydroinformatics side of things, but then even just looking at your research output, looking at all of these different effects that you study, from floods to droughts to landslides. You wonder from the outside looking in, how does one person be able to work on all of these different things? But from your perspective, I'm sure that if you think about the types of models that you use, you might see more similarities than someone looking in from the outside. So would you be able to start off by just quickly laying groundwork for when we think about hydrological modeling? What are the types of approaches we use? What are some of the common problems we try to analyze? And then how are these different models and approaches related to each other?
Yeah, the core is the hydrology. And the hydrological models are the ones that allow us to represent how the water flows into the cycle. So everything is interconnected. In this hydrological cycle, you will see that the saturation of the soil will end into landslides according to certain characteristics, slope and geological formations and so on. The trigger is the rain, which is the saturation. And if you start to make an analysis of how the rain changes in time, well, you can say, okay, either I'm looking at extreme rains that will lead to floods, but also you can look at the extreme rain that will lead to landslides. So there is a connection there, how you model the two things. forecasting can be done also on different lead times. And then the challenge is always how far can I go in the future, how certain I am, how accurate I am, and also where I'm going to do the forecast. This is another question. So all these things are interconnected into the hydrological cycle.
Mm-hmm. And when we start to see these different tools being applied, could you talk about some of the insights that we've gained from considering how these tools have started to be used over time? So, are there any trends that we're starting to see now with increasing results of, say, climate change or human activity in these models? And then with the models themselves, are they allowing us to gain new insight than, say, when we didn't have these advanced approaches with machine learning or even just the raw computational power of analyzing large data?
Yeah, definitely. The advances on machine learning are allowing us right now to be able to see in detail events. In the past, the hydrology has since Plato, you will see that how he used to see the cycle. And in the last 100 years, we have seen advances in they trying to place stations to measure the rain and how it flows and measure the river discharge. And all these things have been evolving in the last 20 years with the boom of the use of remote sensing almost everywhere. And the combination between remote sensing and meteorological modeling and climate change models used to be, I remember in 2003, there were like three models only that everyone was using and everyone was trying to downscale to nowadays they have the same MIP, SEMIP project where you connect and you can have hundreds of models of all the Earth at different resolution with different timestamps, with different ways to assume processes in the atmosphere, even with scenarios of climate change where you can face from the four typical RCPs and your base scenario. So only looking at one model with four scenarios of more than 100 years, you already have a boom of data. You have what is happening in the past and what happened in the future.
Mm-hmm. And when you look at all this, I know in the AI community, it's kind of like a joke that 90% of the time, all you're doing is cleaning the data, preparing the data, finding what to. When you have such a huge boom of like this global data set all the time running for now, it's been decades. Are there issues that you find in figuring out what is most effective to study, in figuring out with all of these different approaches, with different advantages like the spatio-temporal resolutions that you were comparing before? Is there a problem in terms of figuring out what is most relevant for which purpose and which kind of data from which region should we take a look at when trying to develop these models?
Yes, that's very interesting. It is always problem oriented and depends on what you want to do. Every process has a time stamp. If you are going to look into a drought, well, it will not be a matter of 1 hour to know that you are in a drought situation, and maybe hardly one day, but maybe if you start to look at 1 month or 2 months, you start to say, okay, there is an anomaly. And that's how drought is most of the time defined, an anomaly in the availability of water. And then you see that if you want to make an analysis of a river basin for a drought, well, you don't need too much data. And you can use this meteorological information. They are quite accurate, in fact. They are not so bad. They are available at the global scale at a resolution of 12 kilometers, even hourly. So for a drought analysis type of problem, you don't need to do too much cleaning of data. You can just evaluate what is happening, how it is happening, and so on. Of course, one of the first tasks that you have to do is to validate your data. And that's where it comes to you have these large data sets globally, and you have one region that you want to analyze and really see what is happening there. They have probably one station or two, and then you need to validate the data that you have from those global agencies with your local measurements. And just to be 100% sure, but my experiences with the recent developments is the results are quite good for at least for the purpose of droughts. Depending on the phenomenon and the region, if you have a small region, the responses could be 6 hours. This type of data will be hardly efficient for you. You will really need to have more detailed information of the region, better representation of the digital elevation, maybe even having a drone going through the region and identifying the full detail of the elevation model will help. So depending on the problem, you will have to go through different process. But cleaning data, it's not an issue normally when you are working with spatial-temporal if you have these big data sources.
Mm-hmm. And when you were talking there, I started to think about some of the purposes behind this kind of work, because let's just say that you do predict a landslide occurring in an area. You do need quite fast of a response to be able to act on that information. So do you often see that the purpose of developing these types of technologies, it's heavily linked to the application that they have?
Well, what I have seen indeed is some people starting to try to build the models without really going into the literature and finding out how they were, or probably missing the physics into the problem. Like, for example, you can start to forecast an event, but if the event didn't start to happen, how are you going to forecast it? So you're going to say a flood is going to happen, but then they start with the data-driven models to build the model or the machine learning model, a neural network, let's say. And then, no, I reach 24 hours of forecast, and well, but the river basin has only 3 hours response. So you managed to get 18 hours before it started to rain. You are already saying that it's going to flood it or not. But that doesn't go into the mind of someone that says, no, I have to look 20, 30, 40 hours. But the basin is so small that the rain never reached that point. And if your model is using an input that is so far, well, maybe probably there is something wrong. Situations where you say, okay, remember what are you aiming at? If you want to forecast the rain, it's another story, and then bring it to one side and build the physics for your system and feed it. But don't go ahead of what really is happening, because then there is some uncertainty associated to what you're doing. Many people also try to use machine learning without really looking at all the processes that are associated and all the step-by-step parameterizations that you need to do. You're preparing your data, you have already done some sort of statistical analysis where you do your sampling. And in this hydrological science, where your samples are events, you cannot cut them. You cannot say this event comes here, but of course there are certain phenomena that have the previous time steps are attached. And then if you sample values random, well, this one time stamp will not fit with another one. So situations where physics in the data need to be considered before going into the full process. And that I think sometimes they have a model. The model doesn't give good performance. They say machine learning doesn't work. The ANN is giving me good accuracy, but okay, well, you still didn't really do the whole thing. You just went and used one of these free tools.
Yeah, I think when you think about how fast the industry is growing, on the applied side of machine learning, it makes sense that people see the culture of just create a new company, just go immediately into the application, and then a lot of people will be tempted to just apply this new tool to every problem that they see.
Everything, yeah, just went everywhere. Yes, that's very common indeed.
Yeah. But then obviously, as you're saying, it takes a lot of understanding of the actual situation going on. Like, what is this data actually showing us to be able to have the right intuition into how do you actually structure these models? And that's where I think it's very important to think about, as this field grows, what are some of the limiting barriers in place that might be preventing, say, new researchers from making relevant discoveries that might be preventing future applied research from being as useful as it could be? Because one thing to consider here is, like you mentioned, it's kind of rare to have people who understand both how the machine learning works, but then also how the physics of the situation works. One factor there is the number of interdisciplinary researchers here. But then, are there also other issues in terms of funding? Are there also other issues in terms of key technological barriers that are limiting progress here?
Some of the limitations are sometimes related to local data availability, depending on the problem, especially, for example, groundwater problem. Landslides, also you need a bit geology, and also land use changes, which sometimes, you can obtain from remote sensing. But sometimes data is one of the issues. Funds before 2020, I think, were just going slowly in terms of using machine learning in everything. And let's say water, environmental science is not a difference. It was also going slowly. Limitations were associated with, I was telling you, operation system always doubt about the extrapolation capacities, which we know that are limited and data driven, especially when you have human intervention, you have policies. Things can change from today to tomorrow in the operation of a reservoir, and therefore your river stream will change. So those things have been always a limitation for someone to say, should we really invest into doing this type of studies, research, or even build operational systems? But now 2020 has changed. And in the last 6 months, everything that was going in a certain, it was increasing indeed, but was slowly going there, has gone exponential. Funds has grown into everything that is digital, trying to do as much as you can with the data available. Also build up on new ways of trying to obtain data. You will find new funds for building platforms, data visualization, data analysis, and so on. Right now, in terms of funds, I see there are many opportunities in terms of universities, and research is also growing. They are aiming at including this. Before it was just like, okay, you have your department there, it's using machine learning, it's okay. But now it's no, where is the department of machine learning? We need to strengthen, we need to really go, everyone is using, we are not, then let's try to see how can we make this transversal, how they can support other units. So now it's really important. I don't see, I see the challenge that we will be facing in the following months and probably years might be associated more to the different technologies that will be developed in different sites, and each one will compete to each other. That's a natural way that we don't know which one is the right one, and that will probably generate limitations on saying how science in one only one concept is growing, but now it's spread everywhere.
Mm-hmm. And are there also limitations when it comes to, I know you were talking about how with the external interest we see from the funders, do you think that there's a lot of reliance on these external factors, like, say, a government deciding to disclose the right kind of data? And then with government regulations, even, I know with a lot of different AI side of things, there are a bunch of issues with privacy, more so when it comes to things like surveillance systems or things that are directly interacting with using people's as data. Are there issues on that kind of thing when it comes to weather data?
Yeah, depends on the region, and you are right. Some are associated to, of course, with the human culture and so on. Some places are more due to the economics, and if you are, of course, providing information about certain agricultural characteristics, it's of course at the end it's money, and at the end it's production, and at the end is the country how it's developing. And some are very open, they provide almost everything, but some of them they say, no, well, wait a second, well, we keep the information, if you want we can sell it to you, and then you can have more information about the different characteristics and maybe more specific measurements. Cities are a key issue. Cities making the machine learning models for cities, and I am recently working in sponge cities and have like 3 or 4 cases, which is quite interesting how from even the concept of citizen science, with one of the projects we were making a model of a city, I cannot mention which one, but and we did some tests, and the people were measuring the meters, and then we evaluated energy used for pumping, and you can make a database of the performance of the system and the leakage, and we did many things there. Of course, as soon as the manager of the company of the city noticed that we were collecting our own data for a research purpose, he said, this cannot be disclosed to anyone. Why? Because, well, you can find where are the deficiencies, where there were problems with the people, where the leakage is happening. So there were all the inefficiencies will come out. So they protect as much as they can this type of data, especially city oriented. But from the positive side, in terms of research, what you normally do, and if you want to investigate, nowadays everything can be done with remote sensing. You can have a full water balance with only remote sensing images, and you can know how much water is available month by month, almost in any place in the world.
Mm-hmm. And it's amazing to see the progress in this area of research and all of these new applications and technologies that are being developed. And that kind of brings me to the last question I had for you, which was around some of the areas that we still know we need a lot more work on. So what are the areas where, one, we have some known unknowns? We know that there are research gaps here. We know that we need to learn a lot more about this aspect of hydroinformatics. And then two, what are the areas that consistently you see there's not enough attention going to, there's not enough focus being put in researching these specific questions?
Yeah, many things that come to my mind. I would mention the two things. We're talking about machine learning and the hydrology. In terms of machine learning, it's eager data. To use these tools, these algorithms, you really would most of the time prefer to have as much data as possible. The way that the problems have been solved in the past have been by time series that aggregate most of the information. So this space-time concept, to know what happened in one day and the area around it, and maybe another day in another area around it, and another day another area around it, has not been developed. And most of the studies are oriented to what in overall you can do. So if you have, for example, we are looking right now some fields and optimizing the amount of water used in agricultural fields, depending on the agricultural practice, fertilizer, reducing also looking at the optimization to reduce the contamination or the pollution by nutrients. And this, the standards of FAO gives you some, use this agricultural practice and you will reduce your pollution and you will have optimal thing. And that's an aggregated thing. And with that one, you just need an aggregated model. But one of our studies shows that there are very big problems in certain regions when you just apply blindly the thing around the whole region. The agricultural practice, the person that is growing his crops will not get the maximum efficiency, and also probably the pollution is also not reduced. This perspective of trying to build a system that don't take into account the space and time. So the data-driven needs this spatial and temporal data to be able to really be successful. If not, you will end up solving the problem aggregated only with one time series and then end up in a very simple and silly problem. And you will find many publications that only look at one time series and it looks like a financial analysis with only one variable they're running and finding the certainty. Although it can become a complex problem in time series, but I think the challenge for the future are those ones, trying to integrate this spatiotemporal information into machine learning models. That I think is the lack of attention so far.
I think it's very interesting to hear about your perspective on this, because when it comes to your background and having integrated these two different approaches together, it's like you're the first of many, hopefully, because as there's going to be more interest in the machine learning side of things, we are going to see a lot more people who just try to take the tool and then apply it to everything. But then hopefully we also start to see more interest in, well, if we can take this technology that is becoming more and more useful, how do we apply it to different types of problems and specialize in those different areas? And hopefully, as the competitiveness in the industry increases, that's naturally something that happens. But it's amazing to hear about all the progress we've had so far, all of these new capacities that people even a few decades ago would never imagine, but then also consider how much room there still is for growth. So thank you for explaining all of these thoughts you have and your perspective today.
Yep, thank you. Thank you for inviting me.
I think the last thing is, if someone is interested in learning about your work, where might they go?
They can connect to g.corso at un-ih.org. They can go to send me an email or at the website of the Institute, IHE Delft Institute for Water Education.
All right, that sounds great. Well, really appreciate all the insight you provided.
Okay, no, thank you.